Sorry about that. All right, greetings YouTube, Beautiful Mind here. We have this question from Calculus for Business. It comes from section 3.2, question 25. This is on using the second derivative to find the max and min. Okay, so it says for the following function, A, give the coordinates of any critical points and classify each point as a relative max or relative min or neither. Identify intervals over where the function is increasing or decreasing. Give the coordinates of any points of inflection. Identify intervals over where the function is concave up or concave down, and then sketch the graph. Okay. So this discussion is all centered around analyzing the first derivative and the second derivative. Okay. So let's see. We have our original that's q, not a g. Q of x. And we got this x squared plus 25 under x, right? So let's go ahead and find the first derivative. Okay. We'll use the quotient rule. So the bottom, which is this, times the derivative of the top is a 1, minus the top, which is this, times the derivative of the bottom, which is this, all over the bottom squared. So the way I remember that is low d high minus high d low over low low. Okay. Doesn't look like there's any common factors from the numerator, but we can kind of simplify it down some. Okay. So then the numerator will have this x squared plus 25 minus 2x squared. Right. X squared, right? So then it looks like we get 25 minus x squared over this. Okay. I mean, we could do difference of squares there. 5 minus x times 5 plus x. Let's just go ahead and write that just in case it comes in handy. I don't know why I'm so intent on writing a g. So then q prime, we're going to write it as 5 minus x times 5 plus x over x squared plus 25. Okay, so we got this for q prime. So we need the second derivative. I'm probably going to use this guy up here in orange. I'm going to just use that form. It seems like it might be a little bit easier to take the second derivative from there. So then our q double prime. So the bottom is this, times the derivative of the top, looks like it's a negative 2x. So the bottom times the derivative of the top minus the top, times the derivative of the bottom is what, a positive 2x, all over the bottom squared. Wait a minute. I need to back up. So the bottom times the derivative of the top minus the top times the derivative of the bottom. I forgot to add my squared here. Okay, the bottom squared. Okay, so that means there's a squared here. Oh man, that looks like it's going to add a lot more to it. That means this is squared. That means this is squared. Okay. So we made that adjustment. And then now when we go to find q double prime, so the bottom is now this guy. The derivative of the top is a negative 2x minus the top, the derivative of the bottom. So I'll do the derivative of the bottom on its own because it's not right in this over here. So I'm gonna have to get rid of. We'll fix it in just a minute. So we just need to take the derivative. We got this x squared. I'll do it in orange. X squared plus 25 quantity squared. We need to take the derivative of this guy. So find d by dx of this. I'm just doing it off to the side, kind of out of space, and it's just easier to isolate it a bit. Okay. So then this derivative is going to be 2 x squared plus 25 times 2x. I guess that's it. Okay. So this needs to go, oh, okay. So what I'm going to do, shrink all this down a bit and rearrange it so that we can get it all to fit. So let me get rid of the error. Okay. I'm going to duplicate this guy, put it where it needs to belong. And then there's another adjustment we need to do. We'll get it in just a moment. Okay. Just going to rearrange the order just a bit. Okay. And then all over the bottom squared. So we'll capture it like this. Okay. So I think we caught all the errors. So let's try to go and simplify. Now let me highlight some common factors here. Let's see. We got a x²+25. We got 1 here. We got 1 here. 2x. Okay. So there's a 2x here and a 2x here. Okay, those seem like those are the common factors. So let's factor those guys out. Okay, so we know both terms look like they have at least one of the, and I'll do it in blue so it's a little bit easier to track. x²+25, okay, and then we can factor out a 2x. Okay, now from that first term we still have an x²+25 left over, like this. If we factor out that 2x, we're left with a -1 minus, it looks like the 25 minus x² persists. Okay. We use that x²+25, we use that 2x, so the only thing that's left there is a 2. Okay. And then all over, I'm going to leave it as x²+25 to the power of 4. Okay. All right. So the blue and the green are going to persist. I'm just going to bring those guys down. Matter of fact, I'll just duplicate them. Duplicate. Okay. We're just going to let those be. And we're going to simplify the part in black to the right. So let's see. We'll have a -x² minus 25. Okay. We're distributing a -2, so that's going to become a -50 plus 2x². Okay. All over. Okay, we're going to get some cancellations going on. We get this x²+25 to the power of 4. Okay. So this x²+25 cancels at least one of those guys, so we have 3 left over. Okay. 2x² minus 1x² is just x². So now on top, it looks like we have this 2x times 2x² minus 1x² is just x² minus 75. Okay. Over x²+25 to the power of 3. Okay. All right. So let's try to get all of our components side by side so we can use them as a reference. Here's our original Q. Let's copy and paste right here. Paste. Okay. Let's get a copy of Q prime from, I guess I'll use this guy. Copy and paste. Okay. And then let's get a copy of Q double prime. Copy, paste. And again, this is Q double prime of x, right? So that sometimes those second derivatives, it just takes practice. You give yourself plenty of space. Maybe if you have access to like a whiteboard, work there. But you just kind of want to write big, take your time, you know, things of that nature. I'm just going to go with this for now. Okay, so we got our Q prime, and our Q double prime. So we can now use them as references and things of that nature. Let's kind of backtrack a bit. Okay, so we want to find the critical points, right? So the critical points are going to come from the first derivative, right? Those are going to be those values of x that make the first derivative either 0 or undefined, okay? So for part A, we basically want to set the derivative. We want to find the values of x that makes the first derivative either 0 or undefined. The values of x are going to make q prime 0 are going to be the x's that make the numerator 0. So if I set the numerator to 0 and solve, we're going to have 5 minus x times 5 plus x equal to 0. So then x equals plus or minus 5, right? Because if we plug in a -5, we get a 0. If we plug in +5, we get 0. So those are critical values from the numerator. And then the values of x that's going to make q prime undefined are going to be any x that makes the denominator 0. If we focus in on the denominator from q prime, we have a parabola. Let me think. Like if you, okay, long story short, there shouldn't be any value of x that's going to make that guy 0. We can just test it real quick. If we set the denominator to 0 and solve, x² plus 25 to the power of 2, if we set it to 0, we can take the square root on both sides. We'll get x² plus 25 equals 0. Subtract, we get x² equals a -25. So there's no real number that's going, when we square it, that's going to give us a negative result. So there's no value of x that's going to make the denominator 0. So I'm just going to get rid of that just to kind of, I just wanted to include that a little bit, but we don't need it. So the only critical values we get from the first derivative are plus or minus 5. So then we need to see, okay, are those like local max or local mins? So let's go to our number line. Say this is our positive x. Oops. Come on. Okay. Say this is our positive x here, all right? Here we have our -5. Here we have our +5. If we want to consider q prime, these guys are going to make q prime 0, okay? So we want to, like, basically these critical numbers break the number line up into like 3 regions. We got this region A, region B, and then region C. So we want to choose a point from each of these regions to test in q prime, and then we're just really just trying to determine if q prime is positive or negative. So for instance, in region A, we can choose a number like -6. If we plug -6 into q prime, all right, if we plug -6 in, this factor, this guy is going to be positive, right? This guy is going to be a negative. And I think this guy is going to be positive. So a negative divided by a positive is ultimately negative. So we're getting that over here, q prime is negative, which implies the original function is decreasing. In region B, we can plug in 0 into q prime. If we plug 0 into q prime, this guy is positive, right? This guy is positive. This guy is positive, right? So we're getting that q prime is positive in region B, which implies the original function is increasing. So that identifies this -5 here as a local minimum. Okay. Let's choose a value in region C. So when x is 6, if we plug 6 into q prime, this guy is negative. This guy is positive. This guy is positive. A negative divided by positive is negative. All right, which implies the original function is decreasing. So that identifies this as a relative or a local max. Okay. All right, so let's go back to the original question. Okay. Give the coordinates of any critical points and classify each as a relative max or relative min. Okay. So we're saying that we have a relative minimum when x is -5, a relative max when x is 5. We just need to find the corresponding y from the original. So let's see. So if we plug -5 in, q of -5, that's a 50. -5 divided by 50. So then q of -5 looks like it's a -5 divided by 50. -1 over 10 looks like it's a -0.1. Let me check something real quick. Let's just go here. I'm gonna go to my y equals. We're gonna say x divided by x² plus 25. Okay. Clear. I want to evaluate that function. When x is a -5, we should get like a -0.1. Okay. And then if we plug 5 into the original, 25 plus 25 is 50. 5 over 50 is a positive 0.1. Okay. All right. Oh well. Give me just a moment. Hang on. Oof. Sorry about that. Okay. Okay. So then we're getting a relative minimum value of -0.1 at x equals -5. And then we're getting a relative maximum value of 0.1 at x equals +5. Okay, so these are the results we got for part A. Okay, so then for part B, it says identify the intervals where the function is increasing or decreasing. So we've done that already from right here. Okay, so let's just capture those results. So for B, Q is increasing as x goes from -5 to 5, -5 to 5 in open parentheses. And then Q is decreasing basically over regions A and C. So as x goes from -infinity up to -5, and as x goes from 5 to infinity. We do the open interval here. Okay. All right. Okay. Where is the question? There it is. So then C, give the coordinates of any points of inflection. So the points of inflection are going to come from our critical values from the second derivative, right? So any value of x that makes the second derivative either 0 or undefined, okay? So let's start by setting the, again, a fraction is going to be 0 when the numerator is 0. So we're going to start by setting this numerator to 0 and solve. Let me just copy and paste. This is part C. Okay, we want to set this guy to 0 and solve. So then either x equals 0 or 75x equals plus or minus the square root of 75. X equals, what is that? 25 times 3. plus or minus 5 root 3. Okay. So we got a total of 3 critical values from the zeros. Let's see if we can find any x that makes the denominator 0. Okay. That's what's gonna, a fraction is gonna be undefined when the denominator is 0. So let's just set this guy to 0 and solve. Let's copy and paste. Okay, we want to set this equal to 0 and solve. We can take the cube root on both sides. So that should give us x² plus 25 equals 0. Same kind of deal before, right? Because we're going to have x² equals a negative result. We're not going to find a real number then when we square it to give us a real result. So we're not going to find the value of x that makes the denominator 0. So I'm going to just get rid of this for now. Okay, so we got 3 critical values that we need to test. So like for instance, if this is my positive x, okay, positive x is here. Here's our 0. Here's our negative 5 root 3. Here's our positive 5 root 3, right? So this breaks the number line up into 4 regions. We got this region A, region B, region C, and region D. Let's just do green. I'll just try to be consistent with my colors. Doesn't really matter. Okay. All right, let me see. So we want to analyze the second derivative and basically choose test values in each of these regions to see how the second derivative is behaving. So Q double prime. So for instance, in region A, 5 times the square root of 3. So negative 5 times the square root of 3. So that's like, let me just kind of write down that decimal. It's approximately a negative 8.6603, okay? And so that means this guy is a positive 8.6603, okay? So that negative, that 5 root 3 is kind of close to 9, right? So we could choose 9 itself. I'm just going to choose 10, right? So let's choose negative 10. If we take negative 10, and then what I'm also going to do is go here to my y equals, and I'm going to plug in my second derivative right there. Okay. All right. So then my numerator is this, let's just do this, 2x. We got x² minus 75, okay. And then divided by x² plus 25 to the power of 3. Okay, I think that's good. So that way we can just use this to evaluate, okay? So then here, we said we want to evaluate that function when x is negative 10, okay? We're just really concerned with the sign. We got a negative result, okay? So here, just need a little bit of space. Okay. So here, when we plugged in negative 10, we got a negative result, which implies the original function is concave down. Okay. If that's close to negative 9, we can choose something like negative 3. So let's plug in negative 3 into the second derivative. We got a positive result, right? We got a positive result here, which implies the original function is concave up. Okay. So we do have a point of inflection at x equals a negative 5 root 3. Let's choose a point in region C. I think we chose negative 3, so let's choose positive 3. We plug in positive 3, we got a negative result. We got the second derivative was negative, which implies the original function is concave down. So another point of inflection. And then let's choose 10. We got a positive result here in this region, which implies the original function is concave up. So we got 1, 2, 3 points of inflection. Okay. All right, let's go back and answer the original question. So give the coordinates of any points of inflection. So we just need the corresponding y's. So we identified our 3 critical values, all tested positive as points of inflection. So we just need to find the corresponding y. I kind of need a copy of the original. Okay, I'm gonna just copy and paste. Paste. Okay, I'll use that as a reference. All right, so then x equals a -5√3. Okay, so then q of -5√3, let me see, equals, we got this -5√3 squared plus 25. Let me clean it up just a bit. Under -5√3. Okay, we're gonna let's just go ahead and simplify that. Positive 75, right? 75 plus 25 under this -5√3. Okay, 100. Okay, -√3 over 20. Okay, so one of the coordinates we got was a -5√3. Let me back up again. -5√3, comma -√3 over 20. All right, it seems to be some symmetry at play here. Let's plug in 0 into the original. So then, and for whatever reason I keep writing G. These need to be Q's. Q. Okay. We want to evaluate Q of 0. Q of 0 looks like it's just going to be a 0, the origin. Okay. And then Q of a positive 5√3. 5√3 squared plus 25 under 5√3. Okay. 25 times 3, 75. So we have 5√3 over 100, √3 over 20. Okay. So our 3 points look like it's that. It's the origin and 5√3 comma √3 over 20. Okay. So these are our points of inflection. I'm gonna just label it our points of inflection. Okay. So that was what, part C? Yeah. Okay, give the coordinates of any points of inflection. Identify intervals over where the function, and we've done that part as well, where the function is concave up or concave down. So I think that's part D right there. This is basically it right here. I'm just gonna, do I have space? Yeah, I'm gonna just copy and paste. I know, I'm gonna use it as a reference. Copy, we're working on part D. Let's paste. And what I'll do is shrink it down, because this basically is answering part D, this image here. Okay. So then part D, our intervals. So we can say that it's the original. So Q is, I'm just going to label it as concave down. Concave down is regions A and C. So as x goes from -infinity up to -5√3, and as x goes from 0 to 5√3, the open interval, right? And then Q is concave up as x goes from -5√3 to 0, the open interval, and then +5√3 to infinity. Okay. So these are the intervals of concavity. And then I think the final thing is to put all this together. Graph it. Sketch the graph. Okay. So what I'll do, see if I can get my graph paper going. I need a text box. Oh, here it is. Chose the wrong option. There we go. All right. Oh, try that again. And I need the space. There we go. Okay. Can we, I need a copy of the original, this guy. Our y-intercept, if we let x be 0, it looks like it's the origin. Our x-intercept, okay, so it looks like the x and y-intercepts are both the origin. Okay. What else do we have? So from A, we got a relative min of -0.1, relative max of 0.1. The original function is increasing as x goes. Okay. Okay. C, points of inflection. We kind of need those decimals. I am going to do like this, clear. 5 times the square root of 3, 8.66. Okay, so let's do, I'm gonna just do these in purple. So this is approximately like a negative 8.6603. 6603. Okay. So this one should be a positive 8.6603. Okay. Let's get this root 3 over 20. Square root of 3 over 20. 0866. 0866 negative 0866. Okay. Just trying to get a sense of like where these guys are on the graph. These are our points of inflection. Okay. I'm just trying to get it. I'm also trying to get a good window. Our x values, it looks like we need to go at least to 10. Our y values, we got some small decimals there. Decimals there. 0.1. Man, I hope we didn't make any mistakes. Still kind of close to 0.1. Check one other thing. That's based on our x values. So it looks like for our x values, if we go to like plus or minus 10, we should be fine. For our y values, it really looks like it's only going up to like about 0.1. Okay. I have to do a little bit of back and forth to capture everything. So say this is like our origin. And there's more we could do. We could do a test for symmetry, and because it looks like we do have some symmetry at play. I kind of want to let this be like my -10, and I'll come back and adjust things. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Matter of fact, I'll just move it to there. Just to be 10 clicks away. 1, 2, 4, 6, 8, 10. Okay. 2, 4, 6, 8, 10 is here. I lost it. 2, 4, 6, 8, 10 is here. Okay. Now our y values look like it went up to like plus or minus 0.1. Let me see if I did 2, 4, 6, 8, 10. So like if I let this be my 0.1, 2, 4, 6, 8. That did not behave the way I thought it was going to. 2, 4, 6, 8. So I just got to go a little bit off, about here. This is a negative 0.1. Okay. Okay, so let's put all this together. Say this is my positive x. Okay, something like that. Okay, say this is my positive y. Okay. All right. So let me see. We went by 2's. So this is like it's not 0.2. It's like a 0.02, 0.04, 0.06, 0.08, and then 0.1, 0.02, 0.04, 0.06, 0.08. These guys are negative. Okay. And then here, I'm just going to go by 2's. 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. 2, 4, 6, 8. And let's just be consistent. That's a 10. 2, 4, 6, 8, 10. These guys are negative. Okay. This is the origin. Okay. Okay, I'm going to change this to this one. Okay. All right, so now let's just go part by part and add it. Let me see. Do we have any vertical asymptotes? That's going to occur with the denominator 0? No. I don't think we have any asymptotes. So, well, not a vertical. Horizontal, it looks like y equals 0 will be a horizontal asymptote because the degree of the numerator is smaller than the degree of the denominator by 1 degree, or because the degree of the numerator is smaller than the degree of the denominator. So it looks like we do have a horizontal asymptote of the x-axis, y equals 0. Let's go ahead and capture that. Okay. So we'll do it in blue. Horizontal asymptote. Let's thicken it up just a bit and make it dashed. Okay. And that's y equals 0. Also, usually when I'm doing my graphs, I do like to start with intercepts, and I tend to like to start with the y-intercept. Where's the y-intercept? So the I think the x and y-intercepts are both the origin. So with horizontal asymptotes, you can actually touch those and be okay. You can cross those. So it looks like we do have the origin 0, 0 as both our x and our y-intercept. Okay, we're gonna just kind of piecemealing it. Okay. Let me see. So now from part A. Okay, so we had a relative minimum value of a negative 0.1 when x is negative 5. So negative 0.1 at negative 5 and 0.1 at 5. So negative 5 comma negative 0.1. Okay. So negative 5, negative 0.1 puts us like here. So negative 5 comma negative 0.1. This should be a relative minimum value. Okay. And then we also had what, 5 comma 0.1. We could do a test for symmetry. If we do our test for symmetry, it looks like we have y-axis symmetry. So when we get a point on one side, it looks like we're also getting a point on the other. 5 comma 0.1. I just need to confirm the test. I just haven't done it. 0.1 is here. So 5 comma 0.1. Again, that should be a relative max. Okay. Like, again, there are so many other aspects that we can incorporate, especially pulling from college algebra. I'm just trying to keep it to like the bare bones. Okay, so from A, let me go back to A again just to make sure, right? So we got the relative max, we got the relative min. From B, we have the original function is increasing as x goes from -5 to 5. So from -5 to 5, I'll capture that in blue like this. The function should be increasing, something like that, right? We had the original function was decreasing, basically on either sides, right? So on the far left is decreasing and on the far right is decreasing. So we only had one x-intercept. So we have that it's decreasing over here and it's decreasing over here. Okay. So let's keep going. I think that was B. All right. Okay. From C, where is C? Where's our conclusion from C? Points of inflection, right? So that -8.66. So it's like -9, -0.085 essentially. So -9.085. So it's about here and here, right? So we have this. That's a point of inflection. Point of inflection. -5√3 negative. Okay. So this is the ordered pair. -5√3 -√3/20. Okay. And I'm gonna just label it. That's one of our points of inflection. Okay. So we have that it went from concave down. Okay, concave down to concave up. Okay, let me see, concave down to concave up. Okay. So I'm gonna make that adjustment here, right? So something like usually with asymptotes, we start close to the asymptote and we pass through, and then it's gonna see how it's going from concave down, right? This region is concave down, the cup is opening downward. This is concave up, this region in the cup is opening upward. Okay, we're gonna let that be. And so basically, let's get our other point of inflection. The origin is a point of inflection. So I'm gonna make an adjustment here. Here we're going from it should still be concave up, and then it should go to concave down. So something like that. Right here, again, the cup is opening upward. Here, the cup is opening downward, right? Concave down. Okay, we're almost there. I know it's a doozy. That's how some of these are. That's the challenge before us. This is why we do unlimited attempts. This is the main reason why I structure it the way it is, because it can get kind of nasty. So I feel like a reasonable offset is unlimited attempts, you know, all the little caveats that we have. And then let's get our other point of inflection. That's like that 9 and 0.085 approximately. So, okay, I see it. I'm gonna get rid of this. 9.085 is about here, and this is going to be 5√3 comma √3/20. Okay, that's a point of inflection. I'll label it. This is a point of inflection. Okay, so it's going from concave down to concave up, and we finish close to the asymptote. Okay, I think we have the general shape. We have the meat and potatoes, points of inflection. I think we're good. So I think it kind of took on the shape. I think we hit all the marks. All right, so let's just connect this with the smooth curve. So what I'll do, and I kind of need to zoom out some, but I'll just work with it. So what I'll do, I'm gonna get rid of these guys because I think we got the shape. And honestly, on my x-axis, I need to like zoom out so we can see it better. But I mean, I could just redo it. I feel inclined to like redo my graph paper. And I think that I am going to redo my graph paper. So just bear with me since we have a sense of what it looks like now. So let's go here. And okay. So, we're going to go ahead and put all this together. I think we got it, but I just want a better image. Okay, so say this is like my origin here, right? Instead of 10, I think I'm going to take the x-axis out to like 30, right? Maybe 40. Let me see. 4, 8, 12. I don't know if that's going to work. Let's trying to do something simple. Let me see. How many tick marks? 1, 2, 3, 4, 5, 6, 7, 8. If that were 8, 5. So what if we went 5, 10, 15, 20, 25, 30, 35, and 40? Okay, that's fine. 5, 10, 15, 20, 25, 30, 35, 40. Okay. I feel like that's a little far. If we did everything based on 10, it'll be fine. 15, 20, 25, 30, 35, 40. I'm just zooming out some so we can get a better window. I think the 0.1 was good. Let me see. 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. Again, this is my positive x in this direction. Okay. And then my positive y in this direction. Again, I'm just changing the window to just get a better window. I wanted this guy to be my 0.1. So this was 0.02, 0.04, 0.06, 0.08. 0.02, this is the origin. 0.04, 6, 8, 10. These guys are negative. These are negative. Okay. That was like a negative 9, negative 85, 0.085. So negative, let me do this. Okay, so we'll get close. Negative 9, negative 0.085 is about here. And that point was negative 5 root 3 over negative root 3 over 20. Okay, we also had the origin. We had this horizontal asymptote. Okay, style a little bit thicker like that. That was y equals 0. We got the origin in there. We had this negative 5, negative 0.1. So negative 5, negative 0.1 is here. Okay. So we also had what, 5.1, which is here. And then 9, and then 8.5 was approximately here. And that is 5 root 3 comma root 3 over 20. Okay. All right, and then let me get rid of this grid paper. Okay, so again, points of inflection, relative min. I'll do my labels again. So this was a relative minimum value. This was a relative maximum value. This was a point of inflection. This was also a point of inflection. And this here was also a point of inflection. Okay. So then if we put it together, with asymptotes, generally you kind of like start close to the asymptote. We're going to do concave down, concave up. Oh, a little sharp. Our points of a concavity change like that, and then we finish close over there. So, okay. So that was an adventure. This is the image that we got in the end. I know it's a little bit crooked, but yeah. Okay. All right. And so with that, we're going to go ahead and end this session here. And from one beautiful mind to another, take care and peace.